Hi, welcome to The Explainer. Today, we are going to tackle a concept that's, it's pretty fundamental to how just about everything you own gets made. It's called Statistical Process Control, or SPC. Now, I know, that sounds super technical, but stick with me, because you're about to see it's a really powerful idea that you can totally understand. So let's start with a feeling I think we've all had. You know that feeling, right? You buy something new, a phone, a car, whatever, and it's just a lemon. It never quite works right, you're always taking it in for repairs, and it's just a massive headache. That exact feeling is why quality control isn't some boring factory term. It's personal. Look, price and customer service, of course they matter. But in the world we live in now, customers demand quality more than anything else. I mean, think about it. If you spend your hard-earned money on a brand new gadget and it breaks the first day, are you ever going to trust that company again? No way. One bad experience can literally destroy a brand's reputation. Quality has become the main event, the ultimate battlefield. And this right here, this shows you exactly why catching problems early is so critical. The cost of a quality mistake isn't just a flat number, it explodes over time. You see, if you catch a bad part from a supplier before you even start, the cost is small. We'll call it 1x. But if you don't catch it until it's on the factory floor, that cost jumps to 10x. If it somehow makes it all the way to final inspection before shipping, now we're talking 100 times the cost. And the worst case scenario, if that faulty product actually gets to a customer, the price of recalls, warranty work, and a trashed reputation can be 1,000 times the original cost, or even more. You've got to find it early. Okay, so how do factories actually do this? Well, to figure it out, let's put on our detective hats. We've got a case to solve, and we'll call it the 4-machine mystery. Our mission, should we choose to accept it, is to investigate 4 different machines and figure out which one is truly the best for our factory. And every detective needs their tools. Our main investigative tool for this case? It's called Statistical Process Control. Really, all it is, at its heart, is using data to keep an eye on a process. It helps us see the difference between just random, normal variations and a real developing problem. This is our master toolkit. Okay, so every good case has some rules, right? Here are ours. The client, our customer, needs us to make a part with a target diameter of exactly 150 millimeters. And they've given us what's called a tolerance, basically a little wiggle room of plus or minus 10 millimeters. So what that means is any part we make that measures between 140 and 160 millimeters is good to go. Anything outside of that is a defect. Simple as that. And here it is, the crime scene. Just a big old table of numbers. We've taken 9 measurements from each of our 4 machines. And if you just stare at this wall of data, well, good luck. It's basically impossible to tell which machine is doing the best job. We need to start organizing this evidence. All right, to crack this thing open, we got to start with the basics. The first clue any detective looks for to make sense of a chaotic scene: the average. It's going to help us find the center of all this data. So let's bring in our first 2 suspects, Machine A and Machine B. We crunch the numbers for Machine A, and its average comes out to 145. That's a little off our target of 150. But then you look at Machine B. Bang, a perfect average of 150. It's hitting the bullseye dead on. You'd think, okay, case closed, Machine B is our winner. But hold on. Just when you think you've got a lead, there's a plot twist. We run the numbers on Machine C, and what do you know? It also has a perfect average of 150. So now we've got 2 machines that are, on average, perfectly accurate. The average by itself isn't enough to tell us which one is better. We've hit our first dead end. Okay, so the average got us part of the way there, but it clearly wasn't enough. Our investigation needs a new clue. We've got to look beyond just accuracy and start digging into consistency, right? It's not just about hitting the target on average, it's about how tightly all your shots are grouped together. And that brings us to our next crucial clue from the detective toolkit: standard deviation. You'll often see it shown as the Greek letter sigma. Just think of it like a score for consistency. It's one number that tells you how spread out all your measurements are.
And here is the most important thing you need to remember. A smaller standard deviation is always better. It means your machine is more consistent, more predictable, more precise.
So with this new clue, we can finally solve the mini mystery of machine C versus machine D. They both had that perfect average of 150, remember? But when we look at their standard deviation, the story becomes crystal clear. Machine D has a standard deviation of just 3.1, while machine C's is way up at 5.4. That proves machine D is way more consistent. So, D is our winner, right? Case closed? Well, not so fast. And this is where the case gets really tricky. We've got a real detective's dilemma on our hands, because it turns out that machine A, the one with the bad average, it actually has the best standard deviation of all. It's the most precise machine. Its shots are all tightly grouped, but it's not accurate. It's consistently missing the target. The others are accurate on average, but their shots are all over the place. So, which is better?
So to finally crack this thing, we need something better. A master tool that lets us see both accuracy and consistency at the exact same time. And folks, it is time to introduce the single most important, most powerful visual in all of SPC, the control chart. Now, a control chart has two sets of lines that you absolutely need to know. First, you've got your specification limits, the USL and LSL. Think of this as the voice of the customer. It's that 140 to 160 range that they told us was acceptable. Then you have the control limits, the UCL and LCL. This is the voice of the process. It's calculated from your own data, and it shows the natural, predictable variation of your machine. This is your secret weapon, your early warning system. So why are these control limits so special? It all comes down to this one kind of magic number, 99.73%. Statistics tells us that for any stable, predictable process, 99.73% of everything it makes should naturally fall between its own control limits. So, if you see a data point outside those lines, that's a huge red flag that something unusual, something special has happened. And that is the absolute genius of this whole system. Your control limits are designed to be tighter, to be inside your specification limits. They're like the rumble strips on the side of a highway. They warn you that you're starting to drift long before you actually drive off the road and create a bad part. It's all about being proactive, not reactive. All right, so we've gathered all our clues, we've learned about our tools, but the central mystery still isn't solved. Let's lay out all the evidence one last time and see exactly where we stand. So here's the final breakdown in our evidence locker. We've got machine A, which is incredibly precise. Look at that low standard deviation, but it's not accurate. It's consistently off target. Then you have the other machines. They're accurate on average, but they're way less precise. It's the classic manufacturing dilemma. Accuracy versus precision. So what do? How do you solve that? Which is more important? How do you weigh these two things against each other to declare a definitive winner? To really solve this case, we need one single score, a number that can combine both accuracy and precision into one powerful metric. But what could that be? And that, my friends, is where we'll leave it for today. The solution to our four-machine mystery lies in one final, powerful clue. It's a metric known as CPK. So you're going to have to join us next time on The Explainer when we come back to crack the CPK code and finally solve this case. See you then.